Hi class, today we're going to learn about the physics of sound. The first thing you have to know is that sound is a longitudinal wave, and it's produced by a vibration in a medium. And a medium is any sort of solid, liquid, gas, air, water, something like that. You have to know that sound is longitudinal. It is not transverse. A lot of people think that sound waves travel up and down, like you taking a slinky and shaking it up and down, but in fact, sound is a longitudinal wave, which means it is like pushing or pulling a slinky. You can see this in this simulation with the tuning fork in the middle of this page, where the tuning fork vibrates left and right, and the sound waves in the air there get vibrated left and right. If you were to actually see air molecules when there's a sound, you would actually see something that looks like this. You would see a wave going from left to right, but if you actually look at any little dot, which is supposed to represent the air molecules, you can see that they kind of just move left and right fractions of an inch. In a sound wave, you should know what a compression and a rarefaction is. A compression is where the air molecules are squished together, and the rarefaction is where the air molecules are spread apart. Sometimes we also call those non-compressions, which makes it a little bit easier to remember. Now, sound waves are longitudinal, but we can draw them almost like a transverse wave. It's a little confusing. What you should know is that in a sound wave, when we have a lot of air molecules squished together, which is a compression, we can say there's a lot of pressure. So we can make a graph of a pressure versus time graph. And we can see that during a compression, the pressure is very high, but during a rarefaction, where the air molecules are spread apart, the air pressure is very low. So we can make a pressure graph, which looks like a transverse wave representing the compressions and rarefactions of a longitudinal sound wave. So don't get this confused. Sound is longitudinal, but we can draw it as what looks to be a transverse wave. Now, humans cannot hear all sounds. We can hear between 20 and 20,000 hertz. What that means is any sound wave that vibrates back and forth 20 times a second to 20,000 times per second, we can hear. But there are sound waves we can hear. So we cannot hear above 20,000 hertz. Those are called ultrasonic waves. And we cannot hear below 20 hertz, which is infrasonic sounds. And I can play you some sounds here. So this right here would be a 170 hertz sound. That's a pretty low frequency sound. But as we start getting lower and lower and lower, eventually that sound will just go away and we won't hear anything. And as I start going up, this is 570 hertz, this is 770 hertz, and right there that's 1770 hertz. So that's a very high-pitched sound, but we could still even hear higher than that. So we actually can hear some pretty high frequencies. Now, animals can hear different frequencies than humans. Dogs can hear higher frequencies than us, which is why there's things called dog whistles. So you blow this certain whistle and a dog hears a high-pitched noise and we hear nothing. Whereas elephants, right here, can hear 16, 17, 18 hertz that we can't hear at all. Now, when we have loud sounds have higher pressure and much lower pressure than a normal sound. So at a loud sound here, the air molecules are super squished together and then super spread apart, and then super squished together, super spread apart. Whereas quiet sounds don't have a huge difference between high and low pressure. So you get a little bit of a compression, a little bit of a rarefaction, a little bit of a compression, a little bit of a rarefaction, and then continuing on. You should also know that the unit for loudness of a sound is decibels. It's like meters or inches or feet. And it ranges from about 0 to 160 decibels. And here's a couple tables showing what decibels are for different sounds. So me just talking right now would be 60 decibels. If I whispered, it might be 20 to 30 decibels. Things that are getting loud are pretty much 100 decibels. When you start to get really loud sounds that start to hurt, that would be 120 to 130 decibels. And at around 160 decibels, that's when your eardrum starts to get some severe damage. Now, the difference between a boy's voice and a girl's voice is the pitch or the frequency of the sound wave. So A boy's voice, or maybe think of an NBA basketball player who's 7 feet tall, their voice tends to have very spread apart crest, very big wavelengths or very low frequencies. Whereas if you think of a girl's voice, they tend to have higher frequency voices than boys, and their waves are super close together. So they have small wavelengths, but a lot of waves, so a high frequency wave. So just like those sounds I just played you, those low sounds had very spread apart waves, and those high frequency sounds that I played had very high frequencies, so very squished together waves. You should know that the speed of sound is around 343 meters per second in air. You should know that sound must have a medium. It must have a material to travel through. So if you were in outer space and you didn't have a spacesuit on, and you were trying to yell to the person right next to you, literally inches away from you, if you were to scream as loud as you could, since there's no air or any material in between you and that other person, there would be no way for the sound to travel. So it would be completely silent in outer space because of the fact that there's no air. You should know, like I said, the speed of sound is about 343 meters per second, but that changes depending upon the temperature of the air or the material it's going through. So in water, it actually goes faster, or in metals or solids, sound actually travels way faster. So the material is mainly the thing that affects the speed of sound. What you should know from your lab that you did last week is that the loudness, the amplitude, or the pitch, which is the frequency of the sound, does not affect its speed. So someone who yells louder or somebody who changes the pitch of their voice is not going to make their sound wave actually travel faster or slower. Now, using the speed of sound, we can actually solve for a couple things. So let's say you're outside and you see a flash of lightning, and you hear the thunder about 4 seconds later. We can actually figure out how far away from that lightning strike you were. Since sound has a constant speed of around 343 meters per second, and you wait about 4 seconds to hear that thunder, you can use a formula from our very first chapter. Distance equals velocity times time, and you can solve for how far away you are from that lightning strike. So in this case, it would be 1,372 meters. If I gave you another problem and I said, in this case, you are now 5 seconds, you wait 5 seconds after seeing the lightning to hear the thunder, how far away are you now? And you can do the same thing, distance equals velocity times time, and you can solve for your answer, which is you are 1,715 meters away from that lightning strike. And what you guys should know is that 1,715 meters is pretty much 1 mile. So in real life, you're outside, there's storms coming, lightning strikes, you see it, and then you wait about 5 seconds to hear to hear the thunder. You are approximately 1 mile away for every 5-second delay. I believe that's about it. I'll stop there. If you have any questions, go ahead and contact me. Thank you very much.